In this algorithm, I'll go over Bellman Ford's shortest path algorithm. We have already looked at Dijkstra's shortest path algorithm, and here is another one, Bellman Ford's algorithm. But this algorithm allows for negative edge weight, as you can see it in the picture. The algorithm starts by receiving the starting node, and in our case it will be node A, and then it goes through some initialization. Every node in the graph will have a distance variable that represents its shortest distance from the starting node. Initially, we'll set everything to infinity, and every node has a predecessor node, and those are all set to 0. It's basically the predecessor node to the current node in the shortest path. Basically, it's a pointer to its parent type of a thing. So once every node is initialized, distance set to infinity and predecessor node set to 0, and then the starting node's distance is set to 0. And once that's done, the main loops for the algorithm start. And if you look at this, there are 3 loops here, 3 for loops here. The outer loop, the main loop, basically is going to be executed v minus 1 times, v being the number of vertices in the graph. For example, for this particular graph, the outer loop will be executed 3 times. There are 4 vertices here, 4 minus 1, that's 3 basically. Then the middle loop, basically, then for every vertex in the graph, what you do, you go to that particular vertex, and then for every node adjacent to that vertex, you basically update the distance of that vertex from the starting node, and also update the predecessor pointer, basically. It's exactly like Dijkstra's algorithm, basically. So for every node, if you can look at this middle loop, for every vertex current v in the graph, so for every vertex, what do? Here's the last loop. For each vertex adjacent to this current node, figure out the value of the alternative distance, right, to see whether it is less than its current distance, and then you update if alternative path distance is less than the current distance, basically. So that's the algorithm. Let's actually apply this algorithm to this particular graph that we have. So the initialization is executed, and starting node is A. For the initialization, every node's distance is set to infinity, as you can see here. And then the predecessor node is set to 0 for every single node. That takes care of the initialization loop. And then the starting node, in our case A, its distance is set to 0. There is the distance of a starting node, it's set to 0. Now the main loop starts, which will execute 3 times, v minus 1 times. So here is the first iteration. And for the first iteration, for each vertex, which we call it current v in the graph, okay, and in this case, current v will be A, for example. And for each vertex adjacent to this current v, for each vertex adjacent to A, we'll look at the edge weight. In this case, it is 5, and then alternative path would be the current v distance, which is 0, so it will be 0 plus edge weight. I'm executing this line, basically. That's 5. So alternative path distance is 5. And then you go through this conditional statement. If the alternative path distance, which is 5, is less than this adjacent node, this B node, distance, which is infinity, that's true, 5 is less than infinity, then update the distance of this node and predecessor's value. Right? So for this 5 that you see here, since it's less than infinity, we are going to update the distance of the node from the starting node, update it to 5, and then the predecessor node is set to A. We have to do this for every node adjacent to A, and the next node adjacent to A is basically C. The edge weight is 7. 7 plus the distance of the current node, which is A. Distance is 0. 0 plus 7 is 7, and that is less than infinity. We will actually update this node C as well. So the distance of node C from the starting node is 7. Predecessor node is A. Right? So this is done for node A. That was basically, we are right here for each vertex current V in the graph. We just did it for A. Now we go back up to this middle for loop and do it for another node. Right? In this case, B. There's node B now. What are the nodes adjacent to B? There's only one node adjacent to B, and that's D. All right. What is the edge weight? The edge weight is 1. I'm right here. The edge weight is 1. What is the distance of current V? The current V is 5, and then 5 plus 1 is equal to 6. Is 6 less than the distance of this adjacent node? Yes, so we will update this adjacent node basically. This is updated right here to 6, and also we'll update the predecessor node pointer. In this case, it will point to B. Right? And then so we go back up to the middle loops. But what I was just doing, I was executing this inner for loop. Right? So I go back up to the middle for loop and then move on to the next node. In this case, it is, let's say it is D. D has no adjacent node. D has no adjacent node, so we'll move on, and finally we get to node C. There's node C. What is the node adjacent to C? It is B. Right? I'm executing this middle, this inner loop for vertex adjacent to the current V. So the current V is this node C, and the adjacent node is B. And now let's see, what is the value of the edge? The edge value is -4, right? And the distance of current node is 7. 7 added to -4, that gives you basically 3. Is 3 less than current distance of this adjacent node? Yes, 3 is less than 5, so you update the distance of B node. Now you can reach the starting node through C, right? So the distance is 3, and predecessor node is updated to C. That's where we are. So what we have done at this point, going through all these, we have just executed the very outer loop. We just went through one iteration of that, right? I just finished one iteration of that. Let me move these things away from here. And after that one iteration, this is the graph that we have. Now we go through a second iteration. So we are in the outer loop, go through the second iteration, start from A again. There it is, for each vertex in the graph. Look at all the vectors adjacent to it. In this case, it will be B, and see whether we can update its distance. Notice that once again we have the weight of the edge is 5, the distance of A is 0, 0 plus 5 is still 5, and 5 is not less than 3, so no change there. The next adjacent node to A is C. Are we updating the distance of C? For now it will be 0 plus 7, still 7, no updates in there. So no updates are done in those areas. Basically, same thing will stay. Move on to node B. Adjacent node to B is D. Is there any update for D? Well, the edge weight is 1. The distance of B is 3. 3 plus 1 is 4. Is 4 less than the current distance of this adjacent node D? Yes. So basically we'll update this D node, which I have it on the next page. So this D node should be updated as we go to the next node. Right there, it is updated. And so we are done with node B. We go to node D. There is no adjacent vertices to D. Move on to C. What is the vertex adjacent to C? It is node B. Are we going to update the distance of node B? Well, we have 7 minus 4, it's 3. No updates. 3 will stay. So after the second iteration, this is what we have for the graph. The distances and their predecessor's node. Now we go for the third time. So the third iteration, we are way back up to the top of the loop, that for loop, outer for loop, and a third iteration is done. Once again, start with node A, look at its adjacent nodes, basically vertices. There will be no update through this 5. There will be no update to C, no update to B, no update to C. Move on to node B, no update to D. The distance will remain as 4. D and C, there will be no updates to D and C. And basically no work is done in the third iteration. During the third iteration, all the distances and predecessors node will remain the same, and we are done basically. So now each node has basically its shortest distance from the starting node. For example, the shortest distance from A to D is 4. And how do you get there? Well, you go through B, because you can trace the predecessor's pointer to go through it. In fact, here it is. What is the shortest path from A to D? Well, it will be D has to go to B, B will go to C, and then C will go to A. So going through 7, -4, and 1, that's the shortest path.